Okay, so from last time we learned about the forces between spur gears, and in this course we actually care about whether the tooth of the gear may fail, and what would be the failing condition of the gear tooth that is bending. Actually, bending uh, is the one of the failure condition for gears. Why is it happening? Because of the unique geometry of the tooth. It's like a cantilever, and for the force coming from the other side of the gear, it comes down along the pressure angle. So from here, this is the pressure angle. Okay? For example, 20 degrees. Okay? And as we mentioned last time, the radial component of the force coming from the other side doesn't bend the cantilever, doesn't bend the tooth. So it won't matter too much. However, for the transverse one, transverse component of the force, that actually kind of bend the tooth. Even though the shaft is rotating while it's moving. Since you have this force coming this way, so the reaction force kind of go the other way. So the structure is always trying to balance out the force coming from the other side as a force reaction. So the material inside is carrying some kind of stress. Okay. From here, you can tell the shape of the tooth is very curvy. If you really try to study the stress distribution inside the tooth, it's very difficult because there's no general equation to derive it. And there's one way to easily estimate the stress, which is shown in this particular slide. Over here on the top, there is a cantilever model, but it's being rotated by 90 degrees. So actually, it's like a cantilever. If you draw this cantilever in the same orientation, we just treat the tooth as a rectangular cantilever. Okay? So over here, we don't care about the radial force, we only care about the transverse force. So it's like there is a WT pushing the cantilever at the edge. Why do we only study the load right at the tip? From last time we know the force, the force coming from the other side may be changing positions. From this particular drawing, you can see that when your mating teeth are shown in this configuration, the force is coming from, if you are standing on the bottom side of the gear, and the force coming on this way, the force is applied at the tip of the tooth, but when the gear rotates to this particular position, you can see that the force is pushing the root of the tooth. So why do we only study the low condition when the force is pushing the top, the tip? Because that's the worst case condition. Right at this particular moment, when we have force that is pushing at the very top, that's the worst loading condition. And for mechanical design, we study for the worst stress condition. Okay? And then, since we already know, we can kind of know the length of the tooth, but it's also very difficult to identify because it's very curvy. So one way to define this length is to draw this particular line from the point of your force and then try to find a tangent line to this particular point A. You see this tangent line? And then over here, we will define this particular length as L. So that would be the length of the simplified cantilever on the right hand side. Okay? Later on, we will make a perpendicular line to here. So the height from this point A to this particular intersection point, right here, the length is defined as x. This x is going to be utilized for later derivation. There will be a geometrical like a equation derivation based on symmetry of the geometry, the triangular geometry. And we will use that to simplify the equation that we are going to do on the left-hand side. Okay? So, a gear has like a width, right? So we said this part is the face, right? And we mentioned the width, the thickness or the width is called the face width, right? And we use the symbol capitalized F to represent the width. And that is basically the thickness of the cantilever. So right here, this is F. And if you draw a three-dimensional, like an isometric drawing of the cantilever, okay? And over here, since you have this point A, on the other side of the symmetry, of the center line, this is the other side of the point A. So from here, you can get like a, it's also width, but observing on this way. So that would be with T. So right here, this is T. Okay? So over here, if you observe the cross section, it's a rectangle with one side in the length of capitalized F and the other side in the length of T. Okay? That's why they have drawn this gray area on the top. That is how they represent the cross section. Okay? So sometimes if you just observe this drawing for the first time, what does that gray area mean? That's only for representing the cross section. Okay? So basically, that's a cantilever. And the curvy shape of the tooth is now being simplified as a rectangular cantilever. Okay? And we will be studying for the stress inside that particular cantilever. And we will use it to represent the stress inside the tooth. So let's take a look how it's being calculated. So over here, we know sigma equals to mc over I, right? And right here, for the purpose of derivation, it's being converted to I over C. And then the moment would be Wt times F. So here that is Wt times F. Because you have a transverse force multiplying the length. That's how much moment this transverse force is generating. Okay? And the rest will be I over C. So C would be, if you study for bending of the beam problem, then you know this part is C. Right? So C is half of the T. So basically, the bottom is half of T. And I would be, now you need to view on the side. And if I call this X direction, this Y direction, so I am bending the cantilever this way. So I am bending this cantilever about this horizontal, like a neutral line, right? So I will be starting for IXX. Okay? So IXX would be 12 over, if this is B, this is H. So it's a BH, I forget which one. Cube of which one? The area, moment. Here's a reminder. Yeah. Here. Yeah. So, no, this is wrong. That was wrong. Here. So, it doesn't show the axis. It's not a good version. This is, okay, this is good. Ix would be BH cube. BH cube. Okay. So I get back to here. So BH cube, right? So in my case, in the cantilever case, now H is T. Sorry. Forget about full screen. Now H is T and B will be F. B is F. So this becomes F times H is T, so T cubed over 12. So right here you will have Ft cubed over 12. And that is, that's a 6 at the bottom, and Ft squared. Okay, so this is the bottom is right here, so I will have Ft squared and I have a 6 on top. Okay, so exactly the same equation that was derived in the slide. Okay, now since this the model that we're using depends on the geometry of the tooth. So it's like you need to make measurements of L and make measurements of T. So it's like when you have a gear, you really need to use some kind of tool to make measurements, so you can study the stress. There's nothing wrong with it, but uh, there's a one way to normalize whatever that is being studied right there, and it's called the Lewis factor. Okay, so this y is called the Lewis factor. So basically, you can apply this particular factor, and later on your stress analysis becomes the equation at the bottom, and that gives you a way to just pay attention to the transverse force, the face width, and P is the circular pitch, Y is the Lewis factor. And then they found Lewis factor can be studied by uh, they have already made measurements, estimations of the Lewis factor. So you can just check for your reference and look for Lewis factor. Okay, so now let's take a look how we can derive for the final equation from the analysis right here. So let's pay attention to two triangles. One is this one. Okay, so it's a L over half of the, and this one. They are triangles in similar shapes. So the ratio of their edges will be the same. So for the small one, the ratio between this part, that would be T over 2. T over 2 versus X. So T over 2 over X will be the same as this vertical line here, which is L over T over 2. So this is not 1, this is L over T over 2. So that equation is based on the symmetry of the geometry, the triangular geometry. So once you have that, you can rewrite the equation in the following form. X equals to this or L equals to this. Now we can plug in those information into the stress equation that we derived earlier. Once you plug in, after a certain derivation, you will end up with something right here. Okay? And this particular term So to you can then this can be replaced by x, right? Because x equals to t squared over 4l. So this one is x. So after you replace it with x, then you have an x right there. And they specifically multiply p on the top and at the bottom at the same time because they want to define this Lewis factor in a certain way. So later on, the derived equation looks simple. So they specifically uh, create 2x right here and p times 3 over there. So they want to replace this whole part by a dimensionless factor. So that part is completely replaced by y. So this is a dimensionless factor. Because x is basically some geometrical length right there, and p is the circular pitch. It's also in the unit of length. So length over length, that's dimensionless. So now your stress becomes, here is the unit of force, and F is in the unit of length. P is pitch, so also unit of length, right? And Y is dimensionless. So force over square of length, so it's area. Force over area, that's pressure. So your stress remains the unit of pressure. So from checking the units, you can see it remains correct. And it kind of helps us to observe how this stress is being estimated. And it's this new equation is matching better to what we learned, matching better to the definition of stress. Basically, force over area. Okay, because from the top, that is a more complex equation, and also that requires some method. Okay, so when you get a gear, you kind of need to take measurements. You need to know the length, and you need to know T. So L and T is really depending on the profile of the tooth. Okay, so that's the equation of Lewis factor. And that's due to bending. Bending due to the transverse load, transverse force. Okay, so once we have this equation, what can we do next? Since we have this equation earlier, small p times big P equals to pi. So small p is circular pitch, and big P is what's the name of it? Diametric pitch. Okay. So right here, the big P is diametral pitch. Okay, and they follow this relation. And since from the definition of Lewis factor, okay, so since from the definition, x is a geometrical parameter that won't change its length if you uh, basically for same profile, x is x. So over here, y is proportional to reverse proportional to small p. So because of that relation, y is proportional to small y is proportional to inverse of small p. Okay, so they want to define a capitalized y. Okay, or you can just plug it. They want to define this capitalized y. It should be proportional to capitalized p. Right here. So you can then it's right here. Y is 2x. Oh no, it's actually wrong. Small y is 2x over 3 small p. Okay? And so you can then get a small p equals to 3y over 2x. And you can now plug into the pi equation right there. So small p 3y over 2x times capitalized P equals to pi. So capitalized P equals to 2x pi over 3y. And if you define the capitalized or y in a certain way, if you define in this way, then you can now replace the capitalized P by the capitalized Y. So over here, capitalized P equals to 3 capitalized Y over 2x. So now you can then have this 3 big Y over 2x. So over here, no, this is, I think there made a mistake. 2x over 3p, right? Yes. So small. I made a mistake here. It's 2x over 3y. Okay, that's fine. So when I plug in, this is actually Do it again. So small p is 2x over 3y. Okay? And then, so big P is now 3y pi 2x over 2x. And big P equals to 3y over 2x. So you can cross out some of the terms on both sides. Then you have big Y equals to small y times pi. Wrong. Something's wrong again. Where did I do wrong? Do it again. Start over. So here, yes, this is correct. This is okay. So small p equals to 2x over 3y. Yes. And from small p is 2x over 3y. Okay, big P. Okay, yes. And then 2x 3y pi. Yes. Um, yeah. Oh, where did I do wrong? Let's see. Big P to big Y. Then made a mistake. 2x over 3p is 2x over 3p. P 3y, yes. P 2x over 3y, yes. 2x 3y, yes. P is, yeah. So y. This is weird. This is weird. Let me check. The slide is wrong. So over here, big Y equals to pi small y. The slide is wrong. I don't know why the slide is wrong. So this is wrong. Okay, so this should be it. Okay, I just should be the big Y equals to small y times pi. Okay. So anyway, why do we do that? Because we can then formulate the stress equation into this capitalized form. Because sometimes when we have the gear parameters, we are using the capitalized terms. So let's try to plug in and make sure we're doing this right. So we have stress equals to Wt over Fp small y, right? And the small y equals to capitalize Y over pi. And the small p equals to pi over big P. So you end up with Wt F capitalize Y and capitalize P. Yes. So confirmed. Correct. And that confirms this equation is wrong. Let me just correct it. Okay. So, yeah. So now this is the correct one. Right? Okay. So we can analyze our stress either by this equation or by this equation. Depends on which parameter you have. If you have circular pitch, small one, small p, you can use the equation. If you have diametral pitch, the big P, then use that equation. Okay? So let's go back to earlier the definition of your gear. So what is the easy, which P is easier to get? Actually, the capitalized P is easier to get. It's the number of teeth over the pitch diameter, or inverse of your modulus. The module, not modulus, module. So it's usually when you purchase a gear, you know the value of module M. So if you reverse it, the inverse of N, that's actually big P. So you usually know the capitalized P when you get the gear. And if you try to compute for the small p, of course you can multiply pi, then of course you can compute for it. But using capitalized P, it's a number, it's like a value that is easier to get. Okay, let's get back to the following slide. Now, the only thing that we are not sure is the Lewis factor. So actually, for this textbook, in this particular book, it works with many manufacturers, the manufacturer for the mechanical components. So those values came from the manufacturer. That means when you buy a gear from any manufacturer, they may be providing their own values for it. So the textbook is for your reference. It's not always right. If you buy a mechanical component from some manufacturer, you need to read their document. Okay? So for this particular example in the textbook, you can see the manufacturer already compute for the capitalized Y, the capitalized Lewis factor for different number of T. So now you know they are just like the constant values. Okay? Now, can we already estimate our stress due to bending precisely? Actually, no, not yet. Um, since this is only a very simplified estimation of the tooth, the stress condition of the tooth, and gears will be utilized for various kinds of conditions, and the stress inside the tooth would change. So they realize you can still use this cantilever model, but you need to make corrections depending on what kind of uh, condition, operation condition that you're using. So now we will be looking at how or what would change the stress inside the tooth. So one factor is called the velocity factor. So it depends on different velocity, the stress inside the tooth changes. And most of the, when you see this, when you see equations like this, sometimes you will see different versions of equations. They are mainly because of the units they are using when they embed those factors. Okay, so you can see these numbers right here looks uh, nicer, but there's another version right here looks ugly, like 3.04. Who used a number of 3.005? Who used a number of 6.1? Because the original equation was studied in the feet per minute. So right here, please pay attention to the units. Whatever number you're putting in are feet per minute. Sorry, feet per minute. So they initially performed those experiments in uh, the UK units. So they were defined in such a way. So later on, when others would like to use the SI unit, they just convert all those equations into SI units. That's why you see strange numbers here. They are just direct unit conversion. Okay? So over here you can see that speed, the rotation speed that will of the gear will change the factor. And higher speed makes this K larger. And larger K means what? So I need to show you the final form of the total equation. Let's show you right here. This one. So that was KV, right? So this will be the final form of the stress. KV is right here. Okay? That is proportional to the stress. So if KV equals to 1, that means it doesn't enlarge the stress. But when your gear is starting to rotate with some speed, V, that will enlarge the stress. Okay, so from here you can see, okay, there are some other Ks. K, O, Ks, Km, Kb. We will be looking at those Ks later on. Those Ks originally were 1. Without those Ks, the stress equation is similar to what we got earlier from the Lewis factor. Stress equals to Wt times some Pd over F over J. So it's slightly changed. And we will talk about how come we end up with this a slightly different equation. But the idea is that still you will have something a force over area, and this value will be adjusted by very five different values of k's. So first one, second one, third one, fourth one, and the last one. Okay, and we already talked about the factor of k v. Okay, that let me write it down right here. So basically, we have w t p d f j and 5w. Okay, s and b. We will go through them one by one. And what would be the equation that we got earlier? Here. So we originally have this, or this one, small p, small p and small y. Okay. So now this equation will be adjusted to this particular form. So the first factor will be, this basically is velocity. Due to velocity. If the velocity is 0, kv is 1. So if it doesn't rotate, then it's fine. Okay. Now, basically it's the same equation. Instead, just telling you just multiply kv, right? Same equation. Here, next, let's take a look at the next factor, k. This is for later on. Let's talk about which one. This is k. This is for hardness. Where are the k's? Right here is telling you what is j. So j actually is a y over k f times n. Okay? So p is actually 1 over n. So in this particular equation, you actually have kt f, and you have a capitalized y, and so this is a different n. It's not module. This is different n. So this is n. So this j is replacing the y right there, but being adjusted by two terms. Kf is fatigue, the stress concentration factor. We have learned earlier, Kf. And N is a load sharing ratio. And here you need to compute for more terms. So Pn over Z. So what is Pn? And we now need to know what is Pn and what is Z. Pn is So the gear design is quite complex, many terms. Let's find PN. PN. Depends on here. PN is at the bottom. This is table J, and table J, PN. Z is the equation at the bottom. So PN is right here. So so this is stress concentration, right? Stress concentration factor. Okay, Y we already know is a root factor, and this Pn is Mn is Pn over 0.95 times Z, and Pn is P small n times cosine phi n. Okay, so right here, this should be pitch along the normal direction. So basically normal pitch, and this is basically pressure angle. Okay, so Pn is like a calculation for the uh, uh, pitch on projected along some pressure angle. And Z can be determined by this equation right there. Okay, and it depends on some radius. And A is the earlier we already have this shape, right? We know here is the length, and we kind of did this. Right? Here is X, and here is point A, and here is T, right? So Z can be determined from let me show you the table. Oh, Z by the equation right there. R should be so right here. Whenever you see the subscript of P and subscript of G, they mean gear and pinion. So basically, the smaller gear and the larger gear. Okay. So R should be the radius, just to make sure. Because they use this similar symbol here and there. You don't want to be incorrect. That's this R. So for the Z, let's see if it's the radius of the pitch circle. This is basically radius of pitch circle. Okay, and when you see RB, that's the radius of base circle. Okay, and phi is pressure angle. And this is base radius of the base circle of the pinion, the smaller gear. So in this case, A probably is this. Let me show you what is A. A should be this one. No. Okay, anyway. So all the numbers are given right here. Now there are some other more. Let me show you. We can now take a look at this KV. Okay, this is KO, overload factor. So KO depends on the load condition and how much shock your machine is gonna generate. And if it's not, for example, if you have a punching machine, then you will be like a molding machine. It will be punching on a metal plate and then foaming, like a foaming machine. So definitely inside the machine you have some gear, and whenever you are hitting you're foaming the metal plates, then that's generating a much larger, like a shock of stress. So that will be passing through the entire system. Your whole system will be carrying some kind of shocking load. So if it's like a uniform loading condition, then you just apply one. But if you have a heavier shock condition, then you may need to multiply the stress. So this is about the overload factor. And then Ks is about size. So this is about size. So here you can see an equation in very unique format. So usually whenever you see an equation like this, usually it's built based on curve fitting. Okay, so it depends on the dimensional pitch and the phase width and the loose factor. So if you compute for this equation and apply this power and multiply this constant, you get this K value. Okay, usually this is based on curve fitting. So they have done tons of experiments. They fit this particular curve. Okay, so This is Kn about low distribution. This is low distribution. So what's going on about this one? So from here you can see different size of the phase width. The stress will be distributing on the tooth differently. Okay, so and over here you can see there is a general equation but being corrected by certain terms in the back. And whenever you see something like this, very unique coefficients and some functions, again, another result of curve fitting. Okay, so when you apply this C value and also this C value, plug it into the top equation, then you compute for your low equation, low distribution factor. And over here, there is a like a pre-multiplier here, and it's telling you 1 or point A. So it says crowned or crown tooth. What does it mean? So usually, when you have a gear tooth, if it's very straight, then it's uncrowned. So what is crown? Crown means it's being like shaved at the corner. So some of this part of the material is being removed. So you can, from the top, you kind of see a little bit of curve. So if you crown your tooth, the advantage of this kind of tooth is that you don't have a lot of wear at the corners. Because usually after machining, the the edges of the gear of the teeth are sharper. So you kind of need to wear out the sharp corners. But if you crown your tooth, that will generate smoother operation between the mating gears. But you can see it's actually affecting this low distribution factor. Okay? So we're almost done. This is low. Yeah, there's one last one. K B. Here is actually a table to uh, estimate for the factor z. And again, you see coefficients and then very weird equation. Again, that would be a result of curve fitting. I'm looking for K. Hold on, I made a mistake. Those are K's, not W. Sorry. K. And I'm missing a term, KB. KB is somewhere. KB should be the hardness. Hardness. No, it's the ring thickness. Ring thickness, so it should be somewhere in the back. KB. Here. Rim thickness. So if you have a gear when you have a geometry like this is like it's called the rim. Okay, so it's like at the center of the gear there's a big hole, like a donut. So if the hole is too big, then it's looking like a arch. Okay, so when you are designing a gear in this shape, the stress inside the geometry will be different. Obviously, the geometry become weaker, right? So if MB is the ratio of TR over HT, so TR is here, HT is here. So the ratio of the body part over the thickness, it's like the length of the tooth. So if this is larger than 1.2, so if this part is large enough, then you don't need to worry. But if this is shorter than 1.2, in that case, it's like the body of the gear is almost in the same size of your tooth. It's like a 1.1, like a 1-to-1 ratio, or even smaller. Then the stress will be distributed into the rim, and because it's a weaker body, so the stress, so it's like the tooth needs to carry more stress. That's why you have this correction factor due to the ring geometry. Okay? So, with all these, I've shown you everything that how each terms can be calculated. Then that would be the stress due to bending. Okay? And for our design, usually we are looking for stress smaller than yielding strength, right? Usually that's our design equation. But over here, the limit needs to be corrected as well. So if we go ahead and take a look at the final equation right here, it's telling us this value, basically what I'm showing you here, has to be smaller than or equal to this value. So this is actually the limit, okay? So this whole thing has to be smaller than some limit. It's called a sigma O, or I just call it the limit value, okay? And it equals to some equation, ST over SF, and KT, KR, and YN, okay? So the easiest one, this one is safety factor, okay? And we now need to take a look at what is ST, YN, KT, and KR, okay? So let's go back. KT. KT is a factor based on temperature. Okay, so KT is about temperature. So if the temperature is up to 120 degrees C, KT equals to 1. So usually it's just a factor of 1. KR about reliability. KR is about reliability. So reliability usually is a factor that depends on how much failure you allowed after certain rounds of cycle. Okay, and it really depends on how many nines you need. Okay, if you need more nines, that means usually it's after millions of cycle, you still need 99.99% of reliability. So that means when you have 10,000 gears, you only allow one failure. If that's the case, your KR is 1.5. Okay? Something like that. If you have greater value at the bottom, that means when you move it to the left hand side of the equation, that means your stress become larger. Or if you have larger value right here, that means your allowed stress drops. So when you need higher reliability, the limit of your stress drops. So it's like your design space gets smaller. You cannot carry higher loads. So it's kind of making sense. Okay? Now we are almost done. Okay, this is we need to know what is Yn. So Yn is this equation, this table. So you check number of cycles, and this is called a stress cycle factor. It's like this value changes depends on how many cycles you are operating. So this is like about cycles, and all the values that you are applying is based on some kind of curve fit. Okay. So only thing that we don't know is ST. What is ST? Here, ST is okay. Allowable bending stress. Allowable bending stress. So basically, it will be your yield strength. So ST right here basically is you can use your yield strength. So that's everything. So you estimate your stress in a certain way. However, it varies depending on very different conditions. You have overload, size, ring thickness, velocity, load distribution. You correct them. You also have stress concentration factors. You correct the estimation of the stress in such a way, so you end up with a stress value, and that has to be smaller than your limit. The limit depends on your yielding strength, safety factor, temperature, reliability, and also cycles. So that would be the complete equation for tooth design. However, this is the first kind of a failure for tooth. Okay? So let me get rid of this. There's another kind of failure. It's surface wear. Okay? So I'm not going to cover too much about surface wear because we at the beginning of the semester we didn't talk too much about stress concentration due to contact. So we didn't talk too much about that model. So I'm just going to show you the result. So in the future, if you are interested, or if you need to know, there are two kinds of failure modes. One is failure due to bending. The other kind is surface wear. So they also, this is the equation for bending. Okay, the top is the estimation of the stress. The bottom is the limit. Okay, if you go to the next page, it shows you surface wear. So it's like a stress at the interface. Whenever you have two geometries contact with each other, actually right here, it's the geometry. The objects are just pushing each other really hard. So if you pay attention to that point, the stress right at the contact point is actually higher. It's concentrated at that area. So this is about the concentrated stress right at the contact point. So this contact stress can be computed in a certain way. Okay, some of the terms could be utilized, but some others are not. And you can see the equation is completely different because this is based on contact stress. But I didn't cover contact stress at the beginning of the semester, so I'm not going to talk too much. However, if you want to know, you need to look into the contact stress, the stress model. Then come to here to see how the stress estimation is being corrected by different terms. And the contact stress has a limit as well. So for second type of failure of the gear, it's about surface wear. The idea is to estimate contact stress, which is going to be corrected by different terms, different factors, and that stress has to be smaller than certain limit. And this limit also has a allowable contact stress and also correction terms. Okay, so that would be the second failure mode for the gear. Okay, so that's tooth design. I'm still, actually, I think I'm out of time. I think that's everything I want to cover for gears. So last time we talked about how I specifically want you to know about this particular slide. I need you to know that when you have two mating gears, you need to know how much force is being transferred from one side to the other side. So once you know, then you will focus on one particular tooth, and that tooth will be carrying some stress due to the force coming from the other side of the gear. And we only worry about the transverse component of the force because that will bend your tooth. So your tooth could fail. So today I covered, just quickly introduce what are the factors. And I didn't go through the equations. You can always check on reference books to find those equations. But I just want you to know that it's a very complex analysis for gears. That's why researchers didn't derive analytical equations for corrections. They just perform experiments and then they will tell you, okay, for usual cases, k equals to 1. But when you are doing something further, the stress becomes larger. So when they do enough experiments, they will give you equations or a table or a figure and to tell you how much larger. Okay? So this is like how mechanical design has been done in the past tens or hundreds of years. Usually we start with fundamental of physics, mechanics, derive the simplest equation. Then when the geometry starts to getting complex, we perform tons of experiments and then build models. So the models usually extend the general equation from the fundamental to practice. So those correction factors are the key. So for practical applications. Okay? So that's everything I want to cover today, and I think we need to do the roll call. once you're done, that's it for today.